Assalamualaikum. In this video, we will discuss about fluid mechanics application in Formula 1. We are from 3ZK09A. Our lecturer is Prof. Madya IRTS, Dr. Muhammad Rashdan bin Saad. So our group members are Ahmad Z. Ashraf bin Ghazali, FAZRIL AZIM bin Charudin, AHMAD NABIL bin Muhammad Razali, and AHMAD KAMAL bin Satria Ahmad Shah. What is Formula 1? Formula 1 is the highest class of single-seater auto racing sanctioned by the Fédération Internationale des Automobiles (FIA). It is considered the pinnacle of motorsport and features the world's most advanced and powerful racing cars. The cars are designed and built by various teams with engines supplied by companies such as Mercedes, Ferrari, and Renault. The cars are extremely fast and can reach speeds of up to 220 miles per hour. The F1 World Championship is held annually and is contested over a series of races known as Grand Prix. The driver and constructor with the most points at the end of the season are crowned champions.
Design specifications. Every Formula 1 car is composed of two main components, the chassis and the engine. Chassis. A Formula 1 car these days are made from carbon fiber and ultra lightweight components. The weight must be not less than 702 kg or 48 lbs, including the driver tires, but excluding the fuel. One of the most important qualities of carbon fiber is that it is very strong and stiff. Carbon fiber has the highest strength and stiffness per density than metal or any other material. The strength of carbon fiber makes it the right material for racing teams that need the strong car parts. Racing car parts made from carbon fiber can withstand the high energy forces that a car experiences during a race. The fact that carbon fiber has more strength than metal means that the carbon fiber car parts can go the extra mile. Carbon fiber car parts achieve higher levels of performance than parts made from steel. Another benefit that carbon fiber has over ordinary metal, which is make it the choice in auto racing car parts. It is very lightweight. Carbon fiber is 5 times lighter than steel. Carbon fiber is even less dense than aluminium, which is one of the lightest metals. Thus, carbon fiber has a dual advantage because it is strong but light. The dimension of Formula 1 car must be maximum 180 cm width times 95 cm height. There is no specified number for maximum length, but all cars tend to be of almost the same length. Gearbox. Formula 1 car using a semi-automatic sequential carbon titanium gearbox with 8 forward gears and 1 reverse gears with rear wheel drive. Tires. Formula 1 car have been using smooth tread slick tires since 2009. The tire dimensions of Formula 1 car: the front tire is 245 mm width, rear tires 355 and 380 mm width. So, aerodynamic consideration will focus on reducing the amount of drag generated in the car. The importance of aerodynamic design of a racing car is to get the aerodynamic downforce. The downforce can increase the tire's maximum lateral and tangential forces, resulting in an increment in the car's cornering speed and improvement in the car's acceleration and braking performance. The pressure center we place in the rear part of the car ensures that the front wheels have less maximum lateral force and the car understeers. On the other hand, if the pressure center is placed in the front part of the car, the rear wheel have less maximum lateral force and therefore the car oversteers. For 4 baseline configuration are shown, designed to analyze the influence of flaps and end plates in the aerodynamic and structural performance of the wing. They are based on the optimized bi-dimension 2D 3 elements configuration achieved by George Stens through the analysis of several high-efficiency airfoils and multiple degrees of freedom. The 4 configurations are extruded 900 mm, about 2.95 feet in the span-wise direction, which is the maximum length allowed by the 2022 FIA Formula 1 regulations to the front wings. Additionally, The baseline configurations are employed to carry out the analysis of the front wing structural components because of the complex shape of the 2022 wing. After the structural and sensitivity analysis, the selected wing components are implemented in the Design 2022 Formula One front wing. The main features of this bidimensional configuration. Although the current front wings possess a sandwich composite structure with a fiber reinforced skin and a polymeric interior with inner ribs, this research employs a more conventional structure based on ribs, spars, and skin, similar to commercial aircraft. The internal structure of the wing was submitted to a thorough investigation to analyze the influence of each component in the final structural behavior, the nature of the main stresses and strains, and the influence of the most important design parameters. Firstly, a baseline configuration was designed to obtain a first approach of the wing's structural behavior. This configuration is based on qualitative engineering design and it consists of 5 ribs, 5 spars, and a skin. Once the baseline configuration is established, several designs were made to analyze their performance. Some of these designs are shown in this figure.
The first component to design are the spars, which are the longitudinal beam of the wing. The main function is to avoid the vertical deformation of the wing and to absorb the loads coming from the skin. They are exposed to shear stress, and for this case, the shear modulus becomes a critical factor. The design spar consists of a normal extrusion along the span with direction, whose section is based on an I-beam, which provide to be the best choice in terms of stiffness-weight ratio. The initial number of spars is set in 5 for normal I-section beam and 1 beam in the trailing edge of 10 mm width, whose section matches the airfoil geometry, whose position is mainly placed in frontmost part of the wing for 2 main reasons. First, pressure distribution is higher near the leading edge, and the airfoil S12010 has a much thinner section after maximum thickness position. However, due to the structural behavior of the wing, the trailing edge achieves the highest deformation in the wing, and this is the reason why the last spar become critical component in the structure. Another important parameter of the spar is their size. Due to the aforementioned complex carbon airfoil selected, the size of each spar must be adjusted to the environment. Hence, the most suitable approach to parameterize the size of the spar is to set it according to the vertical line in each position. Lastly, the spar shape is analyzed according to 3 parameters of freedom. The first is root width, head width, and head length. All of them measured as a percentage of the root length. Overall, a total of 324 spar configurations are analyzed. The second component to design are the ribs. They are the transversal element of the wing, whose shape in an airfoil and they support stiffness to the wing. The ribs are exposed to normal stresses of compression. These stresses can be achieved in the pressure coefficient in C, where the maximum load is present in the front part. Besides, the rib near the tip suffer less load due to the loss of aerodynamic efficiency in the wing. The rib analysis is performed in 3 degrees of freedom: number of ribs in the structure, thickness, and circular holes. The last parameter is essential to the reduction in structural weight because the center of the ribs is a region with lower stresses. These holes were also decided to be circular because they better absorb the stresses than sharp geometries such as triangle or square. Overall, a total of 80 configurations of ribs were investigated. It is very important to notice that each rib has a different volume for each spar, set, and skin thickness. Lastly, the skin is the external component of the wing. It is exposed to the high flexion loads which depend on the number of ribs and spars of the wing. The skin of an aircraft wing needs to be resistant to corrosion because the coating increases the structural weight. On the contrary, Formula One wings have a short life expectancy and therefore corrosion is not a problem. The skin was created throughout an internal extrusion of the wing surface and it is designed with 5 different thicknesses. Even if the thickness of the skin is very small, its volume is the highest of all components and thereby it will have enormous importance in the structural design. Additionally, it is important to remark that a bigger thickness provokes a reduction in the section of the reed and spar, which is properly treated the structural design.
Okay, next we move to the theory. As we know, engineers of Formula 1 car have used many fluid theory to make one Formula 1. This is because Formula 1 need to be stable while race. The speed of Formula 1 also faster than another car, so the engineer of the Formula 1 need to design carefully to prevent the car from accident. One of the part that engineer needs to think is a design of spoiler. This is because spoiler is reducing drag force and increase fuel efficiency. From the back border of the roof to the trunk of tail of the automobile, there is a very steep downward inclination for the car right now. Air flowing through the roof while race at the high speed will cause the flow separation. Other than in the part of the Formula 1 car have many different theories that we need to study. One of the theory of Formula 1 car is boundary layer. From this theory, aerodynamic will supply the equation of fluid flow. From the design of body shape of Formula 1, the boundary layer, the turbulent boundary layer features swirls, whereas the laminar boundary layer is quite smooth. Laminar flow produces less skin friction drag than turbulent flow, although it is less stable. The flow across a wing surface boundary layer begins as smooth laminar flow. The thickness of the laminar boundary layers grows as the flow returns from the leading edge. The smooth laminar flow breaks down and transforms to a turbulent flow some distance back from the leading edge. To reduce drag, the transition from laminar to turbulent flow should be as far as on the spoiler as practicable, or a considerable percentage of the wing surface should be within the laminar region of the boundary layer. Low energy laminar flow, on the other hand, tends to break down more suddenly than the turbulent layer. This below picture is present the laminar and turbulent boundary layer. Okay, other than that, the first is that the boundary layer increase the effective thickness of the body via displacement thickness. So the pressure increasing the drag pressure. So the equation for the boundary layer thickness for laminar is 5.0 over square root Reynolds number x. For the turbulent is 0.37 over square root Reynolds number power 1 over 5 x. Okay, so the second theory is flow separation. From the flow of separation, we know some of the point will change in velocity. This phenomenon is also known as separation. This is because velocity will come to stall and the fluid starts to flow in reverse direction. The rear part of the Formula 1 will face this phenomenon. The factor of this phenomenon occur is the pressure distribution, which is imposed by the flow's outer layer. Separation phenomena also change the behavior of the behind Formula 1 car that will affect the flow field around it. The disadvantage of the separation cause a greater weight and less pressure on the rear surface that will lowering pressure recovery. As an engineer, to prevent this disadvantage, we need to modify and make a transition of the flow air from the roof to the rear window need to be smooth. The laminar flow that working as a clean will improve the effective of the Formula 1 aerodynamic. So the boundary layer will decrease, thus bad flow separation will avoided. Lastly, there are several forces that apply to the Formula 1 in the different direction when the Formula 1 car move at the high speed. From our study, there are 6 types of force that acting on the Formula 1, which is rolling resistance, drag, lift, gravity, normal, and motor, but only focus on the drag and lift force. Drag force is the resisting force. This force acts in the opposite direction on the motion of an item submerged in a fluid. Thus, drag force is defined as the force that resists the motion of a fluid-filled body. So the equation of the drag force is d over bracket density velocity square area over 2. The formula of lift force is L over rho v square A over 2.
Next, for the conclusion, aerodynamics has had a crucial impact in the substantial modifications in the configuration and performance of Formula 1 racing vehicles over the previous few decades. In fact, aerodynamics has had such an influence on cornering and braking accelerations and hence cornering speeds that measures to limit performance in the name of safety are now necessary. Downforce is a downward lift force created by a vehicle aerodynamic element, in this example, a Formula 1 car. The same concept that permits an aeroplane to soar above the ground by producing lift from its wings is employed in the opposite direction to provide force that presses the racing vehicle into the track surface, increasing grip. This is known as aerodynamic grip, and it is distinct from mechanical grip, which is governed by the car's mass, tires, and suspension. Aerodynamic devices can only improve downforce while increasing aerodynamic drag, and the ideal setup is nearly always a balance between the two. Drag is simply the aerodynamic resistance or friction encountered by the automobile as it passes through the air. When going at high speeds, the design of the body and the usage of wings are two key components of a racing automobile that may be employed to produce downforce. The second way designers might produce downforce is by the use of air force, usually known colloquially as wings. A Formula 1 wing, as previously noted, is effectively an upside-down aeroplane wing. Downforce is generated by generating a zone of lower pressure air beneath the wing. The quantity of downforce produced by a car's wing is essentially governed by 3 factors: the form of the wing, including surface area and cross-section, the angle of attack of the wing, and the speed of the car. More downforce and drag are generated by a bigger surface area. More downforce is produced when the wing or spoiler has a larger angle of attack. The quicker the automobile travels, the faster the air flows relative to it, generating drag and downforce. As a result, the design of Formula 1 demonstrates that it is closely tied to the application of fluid mechanics. We hope that all of the above points and the information are acceptable to our beloved lecturer, Prof. Madya IRTS Dr. Muhammad Rashdan bin Saad. And thank you for providing us with the chance to investigate and study the use of fluid mechanics in sports. So that's all from us. Thank you, sir.